This matrix is an upper triangular matrix. So this is the main diagonal. And entries below the main diagonals are 0. So this is an upper triangular matrix. So therefore, the eigenvalues are sitting on the main diagonal. So I'm going to just call it lambda 1 equals 4, lambda 2 equals -2, lambda 3 equals 2. Now I just have to find an eigenspace corresponding to each lambda. So I'm going to start with 4. So this will be A minus identity. That means I need to subtract 4 from the main diagonal. So 3, 0, and this will be -6. And subtract 4. Oh, this is going to stay the same. And then 0, 0, 2 minus 4 is -2. Got this. Now I'm going to reduce this. And I can do that. So I can make this entry 0 easily, right? So this will turn into this. So divide this entry by 2, scale it by 2, and then multiply by 3 and add it to that. So this will basically just turn into 0, 0, 1, and I can use that to make this entry 0. This is already 0, and I can scale it back to make this one 1 as well. So this will be +1. Now I can make this guy 0 again using the same position. So this will be 0, and this is also going to be 1. And this will be 0. And now I can turn the middle one 0, because I can just multiply the top one by -1 and add it. Middle one is 0, and I can just move that to the bottom. That's this. Now I can turn this into a system which the middle one is x2. So x2 equals 0, x3 equals 0, and x1 is 3. Therefore, this will give me x1 0 0, and that's just going to be x1 times 1 0 0. So I got my first vector. So basically now I can conclude this eigenspace corresponding to lambda 1 is just going to be one dimensional. So it's going to be spanning by this single vector. And similarly, I'm going to compute the second one. So let me do that over here. So now I will say A minus -2 lambda, so that will turn into 2 identity. I'm going to add 2 to the main diagonals of A, which is going to make this 6, -3, 3, 0, this is 0, this is 4, 0, this is 0, and this is also 4. We can easily just turn this into 1 and 0. So this is going to be completely 0, and this will be 0, 0, 1. And I can use that to make the top number 0. So this will be 6, -3, 0 here. And then scale it by, let's say, by 6. This will be 1, -1/2, 0, 0, 0, 1, 0, 0, 0. Okay, so you got a pivot here, and you got a pivot here. Then you can just rewrite it. So x1 minus -1/2, x2 equals 0, and x3 is 0. And now x2 is free, right? So then I have x1 equal 1/2, x2, x3 equals 0. So then I can write this one as 1/2 x2, and then this is 0. So then will be 1/2, 1, and 0. So that's going to be the lambda 2. So eigenspace corresponding to lambda 2 is basically going to be the span of this vector, 1/2, 1, 0. So that's also one dimension. And then similarly, you find E lambda 3 by forming A minus 2i. Okay, and then reducing this, then you can find space for the lambda equal 3.